And so yesterday we finished talking about the translations, which were just up, down, left, and right, just taking a shape and moving it, but not changing the shape itself. We did absolute value was most of it. Today, now we're going to change the shape, but we're going to do it a very specific way. So we're going to do it by stretching or shrinking it, and we can do that one of two ways. We can stretch or shrink it vertically, and we can stretch or shrink it horizontally. Okay, and then we have a specific scale factor. So we have to say what that number is, so that how much do we shrink it, how much do we stretch it. But to start out with, we're going to just look at, and again, use absolute value because it's easy to see. Absolute value is a really easy graph to see stretching and shrinking with. Some of the other ones are not so easy. So I'm going to start with that. And on the first one, I got it for you here. Here's a parent function, which if we want to plug in the table here, so like if I plugged in -2, the absolute value of -2 is 2, absolute value of -1 is 1, and so on. And I actually plotted the points for you to try to save time, so I just put the points in there to make sure. And all those points are these points right here. And then if you continue it on, you got the rest of the shape. The middle graph, and it's probably easier to look at your paper than it is the video here, or the screen, but it says 1/3 x. And if the order of operations, we're supposed to take an x value, multiply it by 1/3, which is like dividing by 3. We're supposed to divide it by 3, then take the absolute value. And I chose different x values because if I leave these x values, it's not so easy to do. So I chose x values that are easy to use, but also when you start seeing these answers here, like if I plug in -6, what do I get? So think plug in -6, divide that by 3, that's -2, and the absolute value of -2 is 2. So same y value, but it took a different x value to do it. Okay, next one, if I plug in -3, -3 divided by 3 is -1, take the absolute value, it's 1. Kind of seeing a pattern here. I want to turn out the same y values every time, but it took different x's to do that. Okay, if I plug in 0, I get 0, plug in 3 divided by 3 is 1, absolute value of 1 is 1, 6 divided by 3 is 2, absolute value is 2. So in order to get the same y values, I had to reach out further, almost like I had to stretch out and get bigger x values. So I had to stretch out away from 0 to get different, or to get the same y values. So instead of plugging in -2 to get 2, I had to plug in -6 to get 2. So I had to stretch out. And it was horizontally stretching, because see, I'm looking in the x direction, I'm stretching out. So this graph, when I plot -6, 2, which is actually over here somewhere, and plot -3 and those guys, I actually took the original points, which I'll plot those. If I put the original parent function down, this was the parent function. Those blue dots, and notice the blue dot was 2 units away. Now it's 2, 4, 6 units away. It went straight out. This one was right here. It was 1 unit away. Now it's 3 units away. So 3 times as far. This was 1 unit away. Now it's 3 units away. So 3 times as far. This was 2 units away. Now it's 6 units away. So 3 times as far. It's almost like this graph, this parent function. I took all those points and I pulled them away from the y-axis. And now their distance from the y-axis is 3 times bigger. Okay? So I took those points and I just pulled them apart. Okay, so since it was in the horizontal direction, it was horizontal. And since I stretched it out, it's a horizontal stretch. So that action right there is considered a horizontal stretch of the parent function, y equals the absolute value of x. So all those points just got stretched out. And that is a little different, because if you said 1/3, I would think 1/3, that makes things smaller when you multiply by 1/3. But here it had the opposite effect. It stretched out and made it 3 times bigger. So it's like the reciprocal of it. Okay? And like, yesterday, whenever we did stuff, when we did translations that were inside the function with x, it did the opposite of what you thought it would do. Like when I had a +3, that's actually 3 units left. When I had a -4, that's actually 4 units right. This is inside with the x, it does the opposite of what you think it would do. Okay? So what do you think this is going to do? If I have a 2 inside there, what do you think that would do? I would assume multiplying by 2 would double things, but what's going to happen since it's inside with the x, instead of doubling it, what's it going to do? What's the reciprocal of 2? A half. It's going to be 1/2 the distance. So it's going to kind of do the opposite. So if I look at my function here, then this is the graph. Like if I plug in 1 times 2 is 2, -1/2 times 2 is -1, which that's just supposed to be negative. I need to edit that. It's supposed to be a -1. Lucky for me, it turns out the same y value, whether it's positive or negative, but it's still a mistake. When I plug in 0, I get 0. When I plug in a half and you double it, you get 1. The absolute value of 1 is 1, and then 2. So in this case, in order to get the same y values as before, I had to pick x values that were closer together because I was going to eventually double it. So I need to take half the x value to get the same y values. So this is the graph of that. If I put the original function down, remember the original function was this. This is the parent function. The blue is the parent function. And those points that were originally right here, they all got pulled in. And they weren't all the same distance, right? It wasn't like some of them, they were all pulled in by 3 units. It was these here, they were 2 units away from the y-axis, now they're 1 unit away. These, which kind of harder to see, but it was 1 unit away, now it's a half a unit away. So it's not that we subtracted some, we actually multiplied by some, we took half. Okay, so we took half the distance, which since it happened horizontally, these points got moved in horizontally, that's a horizontal. And since it shrank horizontally, because the graph got squished together, that's a horizontal shrink. If we had to give a scale factor, on this one, the scale factor was a shrink of 1/2. It was all by 1/2. The first one was a stretch of what? It's how much do they stretch? Not 1/3. It's 1/3 smaller. What's the reciprocal of 1/3? 3. Yeah, it's a stretch of 3. So this would be a stretch of 3. So remember, the x is always, when you're doing stuff inside the function with x, it's like the opposite of what you think it would be. If it's a 1/3, I would assume it's 1/3. Well, it's actually 3 times. That's the reciprocal. And if I have a 2 inside, oh, it's going to double it. Nope, it shrinks it by a half, the reciprocal. So anything that's inside with the x has the opposite effect of what you would think it would do. Okay. Now, down here I didn't put them all in, but we can go a little bit faster, kind of get the idea, hopefully. But look at my transformations here are, I'm working outside the function, not inside. So original one here, 2, 1, 0, 1, 2. We can graph it. Now instead of having the 1/3 inside with the x, I put on the outside, which all this does now is I'm supposed to take the absolute value first, then multiply by 1/3. Whereas up here, it's supposed to multiply by 1/3 and then take the absolute value. With absolute value, it actually doesn't matter. You can factor stuff out of if there's no plus or minus with absolute values. It doesn't always work like that with other things. But so here, instead of stretching the x's out, I kept the x's constant because I want to look at what happens to the y's. So if I plug a -2 in, because see, I'll have all the x values are the constant, -2, -1, 0, 1, 2. -2, take the absolute value, that's 2, and then times 1/3 would be 2/3. Plug in -1, it's 1/3. 0, 0, plug in 1. 2/3. And then do your best to plot those. So I'm just going to do my best. So I'm going to go to -2 and then up about 2/3. -1 up about a third, 0. Continue that on, it looks something like this. Again, if I put the original points back in here, though, here's the original function's points. Instead of those points moving outward, where did they go? They didn't go out, they went down. Because the blue is the old and the red is the new. You can see those closer. So when I multiply outside the function, instead of pulling them out, I'm going to be pushing them down. So these points went from here to there. They went down.
What makes the points on that one go down, but the points on the third one go instead of up?
The only difference, because
On the third one.
I'll answer your question in 1 second. I'm going to respond to the question and then I'll answer it. Look at the reds, or not the red, but this one and that one. Is there a difference between the graphs? This red and that black line graph for you. Is there a difference between the entire graph? No, but is there a difference between the points? Yes. And that's what your question is. It's what I'm doing to it. If I'm doing it to the x's, they're getting pulled out. Now they're inflating, because you think, well, wouldn't this be a thinner line then? Wouldn't there be points missing? Because you have so many x values, when you thin it out, well, there's infinitely many points between, so it's still a solid line. But here, because I'm multiplying the x by something, it stretches out. Because I'm multiplying the function or the y's by something, it's pulling it down. But visually, no difference at all. Yeah, so you're kind of half right about what you were saying. They're the same thing. I mean, they're the same graphs. But because I had a 1/3 on the outside, I pulled them down. If I have a 1/3 on the inside, I'm pulling them out. Yeah, these two graphs, the red graph and that original graph, they're the same graph visually. They're the same graph. It's just where the points went are different. Instead of pointing the points out this way, I pulled the points down. So if I pulled the points down, that's a vertical change. So instead of horizontal like I had up here, this is going to be a vertical. I can spell vertical. It's vertically changing from blue to red. Now, vertically, did I pull it away from the x-axis or did I push it down towards the x-axis? I pushed it, right? So I shrank it. They shrank down. So this is a vertical shrink. Of what? Of what factor? So all of their y values, what did I multiply by? Because this was at 2, now it's at 2/3. It was at 1, now it's at 1/3. What did I multiply by? It's going to shrink them down. What factor? What do I multiply 1 by to get 1/3? You're right, say it. You're all thinking it. 1/3, right? 1/3, 1 times what is 1/3 multiplied by a third? Yeah, so that's not supposed to be tricky. So if there's a 1/3 out front, it is 1/3. Yeah. Isn't that the answers? You're thinking, it can't be that simple. Yeah, I'm not going to say that. That's too simple. So I'm going to color this in red. So the red graphs, a horizontal shrink of 3 and a vertical stretch of 1/3 produce the same graphs. But they're not produced by the same functions. So we got to be careful on that. And the functions are different, but what's the difference between a horizontal shrink of 3, a horizontal stretch of 3 and a vertical shrink of 1/3? Nothing. They're the exact same thing. So I can squish it vertically or I can stretch it horizontally. I'll produce the same picture. Okay? So this one, if I rearrange this, right now it says y/2 equals the absolute value of x, which is okay to put that. That's kind of leading us into tomorrow's stuff. But what would that be if I just had y by itself? If I move the 2 to the right side, what would it be on the right side? What do I do to both sides? Yeah, multiply it over. Okay. So these are the same thing. It's just the way I gave it to you was not standard form. I said that's important for tomorrow, kind of leading you in some of my references tomorrow. But, so this is standard form now, the right one is. So if I fill out the table, plug in -2, and -2, absolute value is 2, 2 times 2 is 4. Plug in -1, plug in 0, plug in 1, plug in 2. This is the new graph. Again, I'll put the parent function on top of this here. So this first point was here. When I plugged in -2, I used to get 2. Now when I plug in -2, I get 4. So it went up. When I plugged in -1, I used to get 1. Now I'm getting 2. Went up. Notice all these x-intercepts, did any of those change? All the x-intercepts, they're all the same. Because if the y value is 0, what's 0 times anything? No matter what scale you use, 1/3 or 3, it's going to be 0. So anytime you stretch or shrink, your x-intercepts won't change vertically, and your y-intercepts won't change horizontally.
Is there a way to tell the difference between, on a graph, the difference between a vertical shrink and a horizontal stretch without the prior, like, normal y equals x to the x?
If I just gave you a picture and a picture, you can't tell the difference. But if I give you the function, that's what you need. Yeah. So visually, they look the same. Yeah, they'll look the same visually.
With outside the absolute value of the vertical,
Right. Or if it's a square root function, inside the square root function would be horizontal, outside is vertical. Yep. And if it's inside with x, it has the opposite effect of what you think it would do. You know. Yeah. So yeah, you're kind of summed up there. So I'm gonna. If I look at those red graphs, they're the same thing. They're the exact same thing. Now this one, again, the points went up, where these went in. But if they go up, that's vertical. And was it a stretch vertically or was it a shrink vertically? They went up, right? So I pulled them out. I stretched them. It's a vertical stretch of, in this case, they all doubled their y value. So it's a vertical stretch of 2. So I'll never give you a parent function picture and a new picture and say, well, what was the change? Because you don't know if it's a vertical or horizontal stretch or shrink without knowing the functions. We will always give you the function that determines whether it's vertical or horizontal, because so these two look the same. This is a horizontal shrink, which is the same thing as a vertical stretch. A shrink of a half and a stretch of 2 are going to yield the same thing. So it's kind of summing it up down here. And then we'll I'm going to stick with this for today. So kind of ignore those until tomorrow. Don't look at those just yet. So these are standard form. If you have some constant, some c, and you're going to multiply inside the x of the function, those are both going to be horizontal changes. Doesn't matter what the c value is, it's horizontal. So the c value is inside. And if you have the c value outside, so you're taking the entire function times 5, times 3, times a third, that's vertical stuff. So those are both vertical. It's just whether it's a stretch or shrink depends on the value itself. So with horizontal stuff, it's the opposite of what you think. So if I gave you a number between 0 and 1, you think, oh, it's going to make it smaller. But if it's with the x, it's going to do the opposite. It's going to stretch. And if it's bigger than 1, you'd think, oh, when I multiply by that, it makes things bigger, has the opposite effect, it's going to shrink it. The good news is, with vertical, it is what it looks like. So if it's between 0 and 1, it's like a fraction, 1/3, 2/3, 1/4, 2/5, whatever it might be. it does actually shrink it. And then if it's greater than 1, it does stretch it. So if it's inside with the X, it kind of has the opposite effect of what you would think it would. Right? So the assignment then is on Delta Math. So don't go to Math Excel. There is an assignment open in Math Excel, but that's tomorrow's stuff, which you can do some of it if you want. But kind of focus on the Delta Math right now. And the Delta Math's a lot of really cool, like you actually pick up points and you stretch them, like I did with my pen. Well, now you get to do it and pull the points yourself. So if you have any questions on how do I do what I'm trying to do, let me know, because I know Delta Math being different, it takes about 5 minutes just to figure out how do I do the change they want me to do. And after that, they're easy. You know, you can kind of figure out how to do it on the content. But so yeah, we'll do the backside tomorrow.